Hello and welcome back. In this segment, we're going to talk about dynamic memory allocation. So to start this discussion, we have to understand the difference between the stack and the heap. These are the two places in RAM that a C program can put its data. All of our variables up until now, including the arrays, have been allocated from the stack. So these are locally declared variables inside of the functions. These are also called automatic data because automatic variables because the memory is given back automatically when the function returns, and we'll look at that in this segment in some detail. Then we'll look at dynamic memory allocation off of the heap, and specifically we will look at dynamic memory allocation for arrays. And we will use the functions malloc, calloc, and free. And I'll explain what each of those are. So let's have a look now at the slides which describe dynamic memory allocation. So let's start our discussion about the dynamic allocation of memory in C programs by talking about two areas of RAM that are used by a C program. And these are called the stack and the heap, and they're used for different kinds of data. So each IDE will have a way of changing the size of the memory available for both the stack and the heap. And we haven't looked at how to change the size of the stack and the heap in Visual Studio because we, first of all, didn't understand what the difference is between the stack and the heap. And they're set so large as a default that you're not going to run out anyway. So carefully setting the size of the stack and the heap used to be a more important issue than it is now. Let's talk about variables now that are declared inside the functions. These are the variables we've been using so far. They're local variables, and they're allocated from the stack. So we've been using the stack to hold our variables so far. And you probably know that each function's variables are available during the execution of that function. You can't see the variables that are local to the other functions. That kind of makes sense. So the stack, the way the stack is organized is that each function is on the call stack starting with the main, and the variables are stored in RAM based on what function they're declared in. So let's have a look at some simple code. Here's the main function, and there are two variables declared. So here's a picture of our stack over here. We have two variables, var and main var, and then when we leave this function by calling another function, so here's the call to foo, we now go into the function foo and start executing, and the stack, you see what happens. There's another piece of memory stacked on the top, and the memory here has the variables that are available in the method foo. And then when we call another function, you can guess what happens now. The stack gets deeper and deeper, and when you're executing this function, here are the variables that are available to you on the stack. So this is called the call stack, and it always has main at the bottom, and how many functions you're in is how deep the stack is. As we put things onto the call stack, this is called pushing onto the stack, and when we remove things from the stack, it's called popping. So we're going to pop things off of the stack. So what happens when this function is over? We return back down to line 8, and that piece of memory goes away. When we return to here, you notice that our variable foovar with 99 in it is still there where we left it. Until we leave this function and we pop the stack again, and now we're back in the main function, and the variables that we had when we left are still there because they were stored on the stack, even though they weren't available when we were executing the other methods, the other functions. So that's variables that are declared inside of methods are local variables, and they're also called automatics because they give back the memory when the function is over. So foovar, the memory that it took up on the stack, is now returned automatically when that function returns. Now let's talk about the heap. The heap is a chunk of memory that's available to your C program for dynamically allocating, for dynamic allocation. You can go out and get a block of memory off the heap whenever you need it, and this memory is accessed by pointers into the heap. So the size of the heap is also set in the IDE, and we haven't looked at this, and we probably won't because we won't run out. We just have to understand that the heap is a block of memory that we have available to us. So we're going to look at 4 C functions that deal with the allocation of memory from the heap. And we're going to pronounce these malloc, calloc, realloc, and free. So they stand for memory allocation, clear, allocate, reallocate, and free. So free is kind of the opposite of allocate. You go and you grab some of the memory, but you're responsible then for giving it back. These will make more sense as we start looking at how they're used. Those functions are available if you have included standard lib.h, and these are standard C functions that are for dynamic memory allocation. Okay, so when we were using arrays up until now, when we declared an array, we had to specify how many elements that array has. So the inside of the square brackets, we needed to have a constant. That's really inconvenient. Suppose you don't know how big the array should be until the program is running. We haven't had a way until now of doing that. So what we're going to do now is we're going to declare a pointer variable which will be the name of our dynamic array, and I've called this one my dynamic array, and we've said that the size of this array will be 5 elements. Okay, here's the function call to go out and get a block of memory. It's malloc, and then we pass one parameter. The result of this calculation is the one parameter. The argument, I should be saying correctly, this is the argument to the function. So size, which has 5, and now we say the size of int. Remember, the size of thing gives us back how many bytes this takes up. So for us, an int takes 4 bytes of space, and we multiply that by 5. So what we're saying is we want to allocate 20 bytes of space off the heap. Here's a picture of it over here. So there's our array. It's 20 bytes of space, and this function returns the address of the first byte. So malloc will give us, suppose this memory on the heap is at address 1000. It won't be, I just made that number up. So the address goes into this variable which can hold an int pointer. So it should start to be kind of understandable that the name of an array is a pointer to the block of memory that the array is stored in, and the malloc function gives you a pointer to, or the address of, this block of memory that was allocated from the heap. So we can put anything in here that we want. We can put a variable, we could generate a random integer in here, and we could get as much memory off the heap as we want at runtime. Well, as much as is available on the heap. So malloc grabs this many bytes of memory and gives you back a pointer to it. If malloc fails, that means it wasn't able to find enough memory on the heap to give it to you. Then it will return null, which is the same as 0. And we also have to notice that there is junk in the array elements. So if you use malloc to allocate space for an array, that memory will not be cleared. Here's where the memory is. Every 4 bytes of space will be used as an int because we decided that the address returned from malloc will be assigned to an int pointer. The only thing we could possibly be doing here is allocating space for an array. Let's look at calloc now. It's almost the same as malloc, and maybe I should have used it in the first example. It clears the memory for you. So if you are allocating space for an array dynamically, you're going to probably use calloc and allow it to clear all the bits for you. You don't have to. You can use malloc if you want to. Malloc and calloc are pretty much the same, except calloc has 2 parameters. You pass it how many elements you have in your array and what is the size of each element. So we have the same thing that we had on the previous slide, except malloc takes only 1 parameter and we multiplied those 2 together. I should be saying argument instead of parameter because we're passing in an argument to the function. So malloc grabs as many bytes as you ask for, and so does calloc. The only difference is that calloc will put zeros into the array. So there's the addresses that we indicated might be on the heap, the same as we used in the previous slide. Okay, calloc and malloc. They might return null if no memory was available, so you should check for that before you start to use the memory. So here's an example. This is the address that we were, whatever address was returned from malloc and calloc, we assigned to this variable, and we check that address to be null. If the address is null, then calloc and malloc, whichever one we used, failed, and we should get out of the program somehow. So here's a way of getting out of the program: exit, and then some value other than 0. So exit is kind of the method that's been used for a long time in C programs to get out of the program, and if you exit with a 0, that means the program has completed correctly, and if you exit with a negative number, that's supposed to mean that the program is stopping with some sort of an error. Okay, so when you're done using the dynamically allocated memory, you have to give it back yourself. So this is not automatic. The way that the stack works, the heap is more like just a big chunk of memory out there, and you can take some and you have to give it back when you're done with it. So we use a method called free, and you pass to free the pointer to the block of memory that you don't need anymore. And you have to be very careful. If you give back your memory by freeing it, you better not be using that array anymore, because you'll be using memory which no longer belongs to that variable. The worst part of this is that if you do use that memory again, it probably will work until it doesn't. And it makes really hard bugs to find. The memory that the data that you had in your array, your dynamically allocated array, is going to still be there in RAM on the heap until somebody else uses that exact spot. If that takes a long time, meaning you might be using the array after you free it for quite a while and have it work, and then someone will step on that memory. So don't give back the array until you're sure that nobody's going to access that memory again. Okay, let's talk about the void pointer. All pointers are just addresses, so why do we need to have a different pointer type for each of the other types? Well, we started looking at this in the segments on arrays and pointers, and we'll revisit it here in the expression asterisk p++. In pointer arithmetic, we're adding 1 to an address, which really adds the size of the underlying data type in bytes. So if p is a pointer to an int, adding 1 to it would add 4 bytes. If it's a long int, if it's a car, then adding 1 to it would really add 1, because a car is 1 byte. If it's a double, then adding 1 to it would really change the address by 8. Malloc and calloc return a pointer to the block of memory that you have allocated. And it doesn't make sense that there would be a different malloc function for each data type that you intend to use. So these functions return something, a data type called void pointer. And void pointer can be automatically cast to the type that you need. So look at what's happening here. Here's the very first one where we allocated, actually this one is allocating 40 bytes of space and giving back a pointer to that space. This function returns a void pointer. This variable's data type is an int pointer. But that's okay. The newer versions of C allow void pointers to automatically be upcast to int pointers. So this is a pointer to the block of memory that was allocated. Okay, so let's just discuss for a little while what we did in this segment. The memory for variables in your C program is either allocated from the stack or the heap. The stack is also called the call stack, and each function's local variables are available on the call stack during the execution of that function. And those variables, the memory allocated for the local variables, are also called automatics, because that memory is automatically returned to the free space when the function is over. So our variables up until now have been automatics, but professional C programmers will do a lot of allocating their space off of the heap. And the heap is nothing but a big chunk of memory in RAM that the program makes available for your use. So you go out and use that memory by calling the malloc and calloc functions, and when you want to give it back, you call the free function. So the stack size and the heap size can both be set in the IDE. You don't want it too small, or the program will end with some sort of an error indicating that the stack is not working right. And you don't want to set it too large, because that would make your program heavy and it would take up too much RAM in the machine that you're running on. So if you have a commercial application that's going to be shipped to tens of thousands or hundreds of thousands of people, you need to set your stack size fairly carefully, so that your stack size and your heap size, so that you don't waste the user's RAM and you don't run out of RAM. That used to be very tricky. We used to spend a lot of time fine-tuning that when memory was expensive. We tend to just make it big enough now so that we're sure we won't run out. Probably not good programming advice, but in reality that's kind of how people are doing it now. So the stack and the heap. Two different places to store the variables in a C program.